Hello everyone, this is Matthew Nelson and welcome to my new demonstration that continues the previous video about how to optimize an in-asset portfolio. In this video we're going to continue from where we left off with a correlation matrix and further develop the statistics we need and run a simulation that will provide us the efficiency frontier for our 12-asset portfolio. So remember last time we had 10 or 12 mutual funds. Here they are. I want to stress the importance about data validation here. So even though I've always simply copied and pasted these names, anytime you use them, it's not only a good idea, it's basically imperative that you set this up as a validation list so that when these are reused, they will always be identical, and that way you can use the offset and match and VLOOKUP commands or HLOOKUP commands very effectively, because if they are just one single character difference or even the formatting of the cell is different, you might end up with errors. So set this up as a validation table. I'm not going to go over how to do that because in this video I want to focus on further uses of the offset command, including the match and index components to those text commands there, relative reference text commands, and move in hopefully to the Monte Carlo simulation and the statistics. So we have a lot to cover. So let's get started. So before we had calculated our returns for all the assets in the portfolio, and then we set up a correlation table, and for your reference this was the function we used that had its own built-in intelligence so that it knew which row, which range to look for columns and which range to look for rows. It saved us a lot of work by doing it this way, and we're going to do something similar today when we set up the variance table. So in an in-asset portfolio, it's one step further from making the correlation table is making a covariance table that is weighted to the standard deviations of each of the assets. So we're going to do that next. So on the left side here we have our assets once again. And the way I've set this up is that it's simply fetching the names from the other page, the profiles page. And we're using the offset, and I named that range as profile, and then A5 is just using a numerical reference as it goes down the rows. This was the rows input. So the risk is also bringing up statistics from the profiles, and I further developed this to not only have the 3-year total return, which is the publicly available information, we also want to get the risk, which is the standard deviation. We don't want to use 3 years of information for the risk because there's too much statistical noise, and that's why we've only taken data since the beginning of 2011. To find the standard deviation, we use this formula. So standard deviation .s, that means it's a sample. So when you have .s, it means divide by n-1 instead of regular n for a population. Again, we're using this internal logic of the offset function so that the computer will decide for itself which columns it should be looking at. Again, we have our named range return. Those are all the log normal weekly returns from the other worksheet. The row, we want to go one row down because our return range has headers, so we want to start with the first numerical value, which is one row down. And here we're going to use a little bit more complicated logic. We're going to add the match function. What the match function does is, looking at one range, it finds out at what point in that range, how many rows across or how many rows down, columns across, rows down, are we interested in working with. So we want to get the numerical value for the columns as our relative reference point for this nested offset function. And what we do is we want B5, we want to look at the name of the asset we're interested in. And here's another new named range, return header. That is exactly what it sounds like. It is that first row in the return data set that just has the names in the order that appears on those return calculations. So throughout this model, I want to be using these functions so that the order doesn't matter. It will always be in the correct order, the correct arrangement, because it's looking up the name of the fund, not relying on any pre-designated order or arrangement that you've set up previously. So this is a very good fail-safe in case things get shuffled. And we will actually shuffle some things when we put the fixed income funds on the bottom later. So that's the lookup array. Match type 0, that means accurate. So we don't want the one above it or below it. We want to count exactly where it is. In this context, you actually have to put the 0. You can't just leave it as comma. For some reason, it doesn't like that. And subtract 1 to convert from absolute to relative. Count A, that's just like in the previous video. We wanted to count how many point estimates are in our return data set, and that was 93, I believe. This function does the same thing by using the offset, starting at the header, going down 1, and then counting the numbers within 1,000 rows below it. 1,000 was simply a subjective choice, totally arbitrary. Okay, so and then just for review, when you scale standard deviation, it scales to the power of this, or the square root of time. So even though they're log normal, and normally you can multiply linearly to find interest rates across time in a continuously compounded system, when you're talking about standard deviation, you have to use the square root, or the square if you're going the other direction. So we want to multiply by the square root of 52. 52 weeks in a year, we don't want to multiply by 52. That would be inaccurate. Risk scales to the inverse of the square of time. So we want to use times square root 52. Okay, moving on. So here we have other new component is a quality adjustment factor. Let me spread that out a little bit. So as you're aware, we just took a ex-ante look at standard deviation, but our application is actually forward-looking. So what do? We can't naively take the past returns. There has to be a bit of a subjective element, a qualitative element to our expectations for the return, not the historical return, but our expectations. So I set up another validation table. Quality adjustment factors, I just gave them basically report card grades. If I'm bullish on the fund, it will be adjusted by plus 15, and moderately bullish, 7. C is just status quo, I expect it to continue. D, getting in the bearish range, minus 3 and minus 10. This is simply an educational demonstration. I didn't put any research into these funds. They don't really reflect what I think, or I'm not making any recommendations here. They're just arbitrary for the sake of demonstration. So what it does is you select from the list how you feel about this fund in the future. And normally, again, you do your research first, and before you just shot from the hip like I'm doing here for demonstration purposes only. So B is slightly bullish. We want to add 7 points to that. And so this function looks up in that quality adjustment factor table what B means, and then it adds B, essentially that's plus 7 to the 3-year historical return. You can see why that's important in this case is because this fund has had a negative return over the last 3 years, but I want to buy it now because I expect it to do a little bit better. And again, these aren't real expectations, and we're just doing this for the sake of argument. Alright, so now we have a better profile page. We have our basically our baseball cards, our rookie cards for all these funds here. Now we can use them. And the way we use them in a portfolio is by allocation. To allocate, we have to decide the weights of our portfolio. And in this case, the monetary values aren't important, just the percentage values. So because this is a just arbitrary, non-existent portfolio, there's no predetermined inputs here. What we actually want is to just have random numbers. So use the random between function between 0 and 100 to essentially assign shares in that mutual fund. You add up all the shares, the total number of shares across the portfolio, and to get the weights, you divide what each row, E3 there, divided by the sum of these. You can't divide by this previously determined sum function, because as Excel iterates, it recomputes the random number for each one of those. And so the way to get around that is to move that computation down by simply recomputing the entire thing. That's the only way in order for these to add up to 100. So just be aware of that. If you simply divide by this cell, which is the sum, you won't get 100%. It has to be recalculated each time in the function. Alright, and so back to standard finance portfolio theory. We're interested in the weight of the asset times the standard deviation of that asset, and we're going to multiply those values arranged in rows multiplied by the same values arranged as columns. And for each of those products, we want to further multiply by the correlation of that row against that column. So we already have the correlation table. So now it's just a matter of pulling the right data from that correlation table in an efficient way. And to do that, we have a little bit of a complicated function here, but it's really not so bad. Again, what we want to do here is find the appropriate correlation number from that table based on the way our assets are ordered here. And unfortunately, that's not the same order in the correlation matrix. We are free to move these around, and as you see, I moved the bonds to the bottom. Just that makes things a little bit easier. And in this scenario, for the sake of conformity with standard financial theory, these are going to be my risk-free assets. So even though they do have some standard deviation and they are not perfectly, idealistically or platonically risk-free, they will stand in for that purpose just fine, because we're going to graph the capital market line. So let's just ignore those and continue with our equity correlations. Again, we want to program internal logic that will take the appropriate row and appropriate column. So the first two offsets are pulling the weighted standard deviation first as a row and then by a column. So again, it's just the same we've been working with so far, and the same little trick here of when you're working with these rows, you want to lock down the column and let the row float. And when you're working with columns, you want to lock down the number for the row and let the column float across. And so this is going to simply offset 5 columns each time in this allocation table to find the WI/SI number. So when you see this in sum notation, one will be WJ/SJ. But really, they're the same data set. They're just arranged in columns and rows. So that's easy enough and saves us the hassle of making another table. And then finally, we want to multiply by the correlation from that other table. And to do this, introducing a new function here is the index function. Index just tells it how many rows, how many columns, what's in that box. That's all there is to it. So index, we are looking at the correlation array on the other worksheet. And we're going to reorder. Now this is the tricky part. Because we've manipulated the order in our allocation table, so that it now is different from the original correlation reference table, we need to figure out which row and column we want to pull based on the name. So we need to figure out the number of the row and the number of the column by using these two match offset combination functions. So what it does is, first of all, it looks up the name that we want to work with in our portfolio allocation. And then on the correlation table, I've named two new ranges, the headers and the left columns, so the top row and the leftmost column. And that will look up respectively the numerical identity of the column we wish to work with and the row we wish to work with. And that just becomes basically a geometric coordinate in that table. So it rearranges everything for us, so we no longer have to worry about the tables being perfectly in the same order. We can rearrange things at will, and all of it is validated by using the offset function, so that original profiles table will always have the master validation data, so everything is perfectly uniform and always in order, because we're using a logic to look up the names of the funds rather than relying on the layout of our tables. So this is the way to get around the fact that you can't simply use VLOOKUP and HLOOKUP to do this. You have to use offset and index and match to get around this. But basically what I'm doing is a really kind of grown-up version of VLOOKUP. And that's all there is to it. So again, the weight of the I assets, the weight of the J assets times their standard deviations, and then times the correlation. So that gets the weighted variance for that particular asset. And all you have to do then is sum this array, and that will give you the variance. And the portfolio standard deviation is merely the square root of the sum of this variance table. And that's 17.84 in this particular iteration. And the expected return is the weighted return of the portfolio. So we use sum product, this array times this array, and add it all up. So that is the expected portfolio return, and that translates into our x and y coordinate for the efficiency frontier, which is our next step. And similarly, as I mentioned before, these fixed income funds, which are short-term, limited duration, and treasury bonds, will stand in for the risk-free asset, and to make things idealistic and conform to standard financial theory, just ignore the standard deviation on these and let these be on the y-intercept, just for the sake of graphing the capital market line. Okay, so as you remember, these are random numbers. So if I calculate now, the entire portfolio of these 11 looks like, 12 or 11, they will completely rebalance in a random way, different allocations of each fund. And each time I calculate, the computer will calculate the overall standard deviation and return. Now, the next part uses a data table to take advantage of the random number generator and does a Monte Carlo simulation. So to do a Monte Carlo simulation with a model that you want to keep updating, just do iterations of random combinations, set up a data table. And all you do in the data table is to pull the allocations here. These are just the previously determined formulas from the cells. It's just linking to the other cells, really, and the overall risk and return. And this data, all you do to get multiple iterations of these random allocations is to trick the data table into thinking that it needs to input a dummy character. So you can just put it on the top left, this text here, or a blank space. It doesn't really care because those functions involved don't rely on this cell. So it'll go through the entire random number generation process and iterate these various portfolio combinations, 1, 2, 3, all the way down to 5,000. Take my word for it, it goes all the way down to 5,000. Okay, and so once we get our data, we can use the max function to find the best portfolio from our simulation. So you want to find the maximum in efficiency, efficiency being our bang for our buck. We have return divided by risk, so for every unit of risk, what is our return? Okay, simple enough, so the highest one of these, the most efficient. And that should be the tangent point for the capital market line. So to find the best portfolio, well, number one, you want to know what the maximum number is, the maximum efficiency, and then you want to match that number inside this array, the same array we're working with, efficiency, and then subtract by 1 because of the header row there. And once you do that, the best portfolio will show up as the ID number for the portfolio back on the left. I can see that the numbers keep updating, so I've broken one of my own rules here is when you have one of these complicated simulations, it ties up a lot of computer resources, so what you want to do is make sure that it doesn't update the data tables. It can automatically calculate cells, but you want it to tell it to leave the data table alone because unfortunately you can probably hear my computer's fan working a little bit of overtime as the CPU gets busy. Let's recalculate everything just to be thorough to make it interrupted. So we want to calculate, and what it's doing is going 1 by 1 by 1 down to 5,000 times, making these random combinations of portfolios. And apparently it's finished. And so we can see we have almost a one-to-one relationship of risk to return, and that's the best we can do. So that should be the tangent line. And the capital market line, just make a little linear graph here, or we actually, I prefer to use a fit line from a scatter plot. So you need some x coordinates and some y coordinates. So on 0, 0 being 0 risk, we want the risk-free number from the allocation page, and that's the intercept. Y-intercept is the risk-free rate of return. And then we have our best portfolio from here, risk and return, that's connected to these two. And then we want the maximum risk, and that's just pulling from, the maximum return, pulling from these, and the this coordinate has to be extrapolated from the slope of these point estimates. So you can use the slope function and then just scale that up by the difference between these last 2 point estimates plus where it was before. And once you do that, here we go, we can get the efficiency frontier. Let's let the computer think about that a little bit. Okay, let's scale in. So before I scale, this is the risk-free rate on the y-axis. We're no risk. We're guaranteed this is our minimum return. And where you see the red square there, that was the best portfolio. And it does indeed turn out to be the tangent line. And the superimposed green triangle is the same value for the sake of graphing the capital market line, which is just a linear fit line on that scatter plot. So 3 series of data in our scatter plot. Okay, and then these are all the portfolios from our random simulation. And this is straightforward enough to do with 3 assets, but once you get more than 3, you have to rely on these simulations to do so. And Excel can't do this. I believe MATLAB can graph something like this a little bit better, but if you imagine that density here was a z-axis, you can actually see this topographically, and the most distribution is in the center of this mountain. Think of it as looking straight down on a mountain from a satellite. and it slopes down to this point here, and that is the basically our market portfolio tangent to the capital market line. And so you can keep updating and look at the best allocation for your portfolio and move it along to keep it at the efficiency frontier. And this is our normal shape as to be expected. So this is a very powerful tool, and once you get it set up, viewers, very, very useful, and I hope you do use it, with the only caveat being that please keep in mind that we're interested in future expected returns, and it's not good enough to rely on naive ex-ante past-looking data. So that's where quality adjustment factors comes in. That's where your homework comes in by doing research, going to Morningstar or Standard & Poor's and looking at industry research, or reading the International Monetary Fund's quarterly report, the Fed's Beige Book, all these things. Please do your research before investing, as these are not FDIC insured. Also, another thing I wanted to mention, put the link in the video, is that video description, is that there's a new paper that came out through the Nature journal, Nature or Science. They have a new study that shows that during financial stress in the markets, correlations approach one another, and the benefit of diversification is impugned. So very interesting study. They took a look at the Dow Jones Industrial Average for since the beginning and looked at the average correlation and found that during bad times the usefulness of diversification is weakened. So very fascinating study. I'll put the link there in the video. And again, I am still looking for a job, and if you would be interested in considering me for your team, let me know. I'd appreciate that. Again, this is Matthew Nelson. Thank you for watching. Please subscribe, like, and comment, and there'll be links below in the description. Signing off.